little bit of history on this presentation. This started out as a paper we were asked to write about 10 years ago and present at a conference down in Atlanta, Georgia. What we've done is it's basically the fundamentals of rotary screw compressors. And when we talk about rotary screws, we're talking about the ones designed for natural gas service. We're not talking about air compressors or, there's some really heavy-duty process machines. We're talking about your basic, Howden, Frick, Mycom, Sullair, some Gardner Denvers, those kind of machines used in natural gas service. From that presentation, or from that paper, we had to present it down there. This is basically a scaled-down portion of that presentation. Just a brief outline of what we're going to go over today. We're going to use a lot of computer-generated animation to look at how screw compressors work, okay? A lot of the comparisons we're going to use are against reciprocating machines. I'm going to have some homemade video of basically a model of a reciprocating machine that's much more rudimentary than the one Walt's going to talk about next. But basically, we go under the premise that most people understand how a piston moving back and forth in a cylinder, in a very simple acting or single acting cylinder, people understand how that compression cycle works. So as we walk through this whole thing, we'll use a lot of animation and things like that to try and explain how it all works for you. We'll look at the different applications of the machines, what types of gases, pressure ranges, horsepowers, different things like that. The different features of the machines, and again, this is kind of in a comparison against reciprocating. We'll show you a blow-up diagram with a cutaway and just, some of the very simple, very simple breakdown of a screw compressor. I wanted to pass these around. These are just a couple of real simple little models, okay? But they really do just show the meat and potatoes of the machines themselves. Really, the two moving parts you're going to see are the rotors, and that's pretty well about it. Then we'll look at the basic operating principles. And here we're going to spend a lot of time with more computer-generated animation showing how the gas physically goes through the machine, how it's compressed. We'll talk about the capacity control and how the slide valve works within the machine. We'll show you a video on that. We'll walk you through the lube oil system. And again, we'll actually show oil being injected into the compressor and how it's filtered and feeding bearings and things like that. We're going to spend a lot of time looking at three different process flow diagrams. And the difference in these three, there's basically three process fluids that need to be cooled on a natural gas compressor. And I'm assuming an engine drive application here. So what we've got is the engine jacket water, obviously. We have the compressor, lube oil, and the process gas. There's three different methods of cooling the oil and the process gas. These process flow diagrams will walk you through the pros and cons and kind of a working diagram of each of those three. And then as we're wrapping up, we'll talk briefly about some sizing and design requirements. This is more applicable to some of the people who are actually scoping this equipment, specifically some consultants, possibly some production and facilities type people, and then some different options. And, we always get tied up in the middle where, field guys obviously want more options than the guys in town willing to pay for and things like that. So we just try and lay out some of the options and say, here's the benefits of them and things like that. And then just a quick summary as we wrap up. So everybody understands, like I said, a very rudimentary reciprocating machine with a piston going back and forth. Now imagine if you could keep that piston moving in a continuous motion. You'd eliminate any gas re-expansion at top dead center. You'd get much better volumetric efficiencies. Now imagine if you were able to vary the bore and the stroke length of that cylinder. So what we're going to do is we're going to replace the conventional piston and cylinder with a male and female rotor. So what we've got here is basically a female rotor with a number of different flutes in it. And each of these flutes will operate like a cylinder. Then we have a male rotor with a number of different lobes on it. And each of these lobes operates as a piston. The net result, as you can see in that model we're passing around, we apply a counter twist to this, and you end up with a set of helical gears. This is really the heart of a screw compressor. That's all there is to it. And again, each one of these lobes is basically operating as a piston. Each one of these flutes operating as a cylinder. In a lot of the models we're going to walk through today, we're only going to show gas sitting in one of these chambers at a time. Obviously, it's going through all the chambers, but for the simplicity of illustration, we're just going to throw it through one flute at a time. The different applications for screw compressors. These machines can be pulled down essentially to a perfect vacuum. In a past life, we packaged up a machine for hydrogen service that was operating at 1 psia. So as far as mechanically, on an oil-flooded, like a process-type machine like we're talking about today, they can pull well down into a vacuum. A lot of people in Canada aren't doing a lot of that for natural gas, but it's definitely coming. There's a few doing it. It's popular in the States. Suction pressures, in a past life, probably up to around 50 to 70 pounds, and discharge pressures not usually over about 300 pounds. Nowadays, there's a number of manufacturers that take that quite a bit higher. I believe Sullair today is the highest. It's got some frames capable of about 140 pounds suction and up to just over 400 pounds discharge. So gone are the days, the old 15 years ago, the mentality was, well, if it's over about 250 pounds, it's really not a screw application. Okay, so just wipe those thoughts out. There's several machines that are capable of getting well over 300 pounds, and like I say, a couple over 400. The common horsepower ranges. again, with discharge pressure being, kind of the deciding factor on horsepower, when we've only got 400 pounds on the high end, you're not going to see 3 and 4 and 5,000 horsepower screw compressors. The most common range, and there's rules to every exception, exceptions to every rule. Most common range is about 30 to 1,500 horse. Okay, these are going to range on the smaller machines, typical individual wellhead boosters, any shallow gathering systems, very popular in CDM, basically any low pressure gathering systems and things like that. Another popular home we see is people are dropping screw compressors in front of existing two-stage recip machines. So 10 years ago, you might have installed a recip machine in a real mature field where the suction pressure at the time was 100 or 150 pounds. Now, over time, that field started to deplete, things like that. So you're now starting to run into temperature issues in the compressor, and Walt will get into more of this. You're running into rod loading issues and things like that. So a couple of the options you're going to have would be re-cylinder and restage that compressor. It's a lot of money when you start looking at doing it. What a lot of people are looking at now is they're just dropping a screw compressor in as stage 1 of compression, and then the recip becomes stage 2 and stage 3 to get you back up to your 1,000 or 1,500 pipeline pressure, wherever it is. Also, they're becoming more and more popular for heavier gases, solution gas, vapor recovery, treater gas, different things like that. In the old days, people just used screws for sweet gas. As we're getting a better understanding of how they work and things like that, we've got a lot of applications now where they're running in, obviously the sweet's a pretty straightforward one, but much heavier gases, solution gas, treater gas, acid gas machines. In a past life, we did a machine for acid gas. It was 35% H2S and 65% CO2. The compressor itself is a standard oil-flooded machine. The piping and the instrumentation and things like that are obviously built for very corrosive environments. But as far as the screw goes, as long as people understand the process behind them, they can be applied in these much heavier applications, much heavier specific gravity or mole weight applications. The biggest thing we have to look at when we're doing it, you'll find, I think, if you actually go out to bid for a vapor recovery unit or a treater gas compressor, the norm, people always ask for the little rotary vane machines and things like that. What's happening nowadays is, as people are getting better educated on the screw side of things, they're starting to entertain these. And the big thing you need to understand is, in order to use a screw compressor in a heavier gas application, the big thing we need to make sure of is the discharge temperature at, after the compression cycle is done, is well above the dew point of the gas at the discharge condition. So when we talk about the dew point of the gas, there's 2 dew points we worry about. One is the water dew point. So at what temperature is the water going to start to drop out of that gas stream? The second one's a hydrocarbon dew point. So at what temperature do your heavier ends, your C7s and C8s, start to drop out of that gas stream? Traditionally, the water dew point is much more of a concern. The 2 factors that impact that are basically high inlet temperatures will really impact your water dew points. Obviously, the higher the inlet temperature, the more water vapor the gas will hold, the more of a water dew point issue you've got. So if we're coming off a treater at 130 or 140 degrees Fahrenheit, we know that gas is going to be water saturated. It's going to contain a lot of water as far as, pounds of water in the gas stream, and our dew points are going to be quite high. We need to calculate that and ensure that the discharge temperature of the gas stays well above that dew point. Otherwise, water will start to drop out and mix with the oil, and it just makes a nasty combination. Some of the features of the machines. As you can see from the models we're passing around, there's very few moving parts. When Walt shows a blow-up of the recip machines, you can get multi-cylindered machines, and each of them has numerous valves depending on the diameter of the pistons and things like that. So with very few moving parts, you end up with reduced downtime and reduced maintenance costs. Reduced downtime, the net effect to you is higher production revenues to you guys. They're also very good part load capacity, okay, as far as the horsepower savings and just unloadability. Traditionally, people start using the unloaders or the automatic slide valves at around 300 to 400 horsepower and above. Below that, again, just rule of thumb, but the economy of scale is typically people use manual slide valves and things like that below 400 horse. And we'll walk through exactly how the slide valve works. As far as operational flexibility, a single-stage screw compressor can operate, well in excess of 20 ratios of compression. Please don't be misled there that at 20 ratios of compression, we're obviously not as efficient as a reciprocating machine is on horsepower. If you take a 3-stage reciprocating machine, it will use much less horsepower to pump the same gas as a single-stage screw at 20 ratios of compression. What you'll typically find is, depending on the size, if we talk about small machines, a 200 horsepower screw compressor is likely going to cost less money than a 150 horsepower 2-stage reciprocating machine. Just the capital cost. By the time you put, Walt's got some pictures, all the additional bottles and cylinders and piping and cooler sections required in the recip machines, the capital cost of the screws is typically going to be a little bit less. You can also weigh out the cost of fuel, and typically you're weighing that out against the cost of maintenance. On screws, you're typically going to overhaul these machines maybe every 3 or 4 years.